Students, welcome back to the second part of the lecture, and in this lecture we are discussing about clustering, right, one of the techniques of unsupervised learning, and we will discuss mostly about the centroid models. We will know how to divide task or how to divide data actually into meaningful groups based on some similarity. So, let us talk about the conceptual clustering problem. So, what you have? Given you have a collection of unclassified objects or data, and what you need to find out is a means of measuring the similarity objects. That is what it is, right. So, you have given a collection of data and you need to find out a means of measuring the similarity objects. So, how do you do that? You can measure distance, of each object from each other, like. So, clusters or objects such that some standard of quality is met. What is the standard quality? Like maximization of similarity objects in some class, or you can actually find distance between these objects or between these different points. Ideally, we like to represent clusters and their semantic explanations. That is what idea. So, we like to define clusters by certain generality rules, not by numerical rules. Remember this. This is what it is. We do not want to have numerations. We want to have some general rules for the clusters. What you have is that when you do that, when you want to cluster that, it is very easy to cluster things intuitively in 2 dimensions, right, either one I shown you in the last example, or even I shown you in KNN also. But if it not possible in 2 dimensions, the dimensions goes beyond 2, like 3, 4, 5, 10, it can even go to 10,000. Higher dimension spaces will look very different, and probability of random points being closed drop quickly as the dimension grows. This is the problem of, or this is what is known as a curse of dimensionality. So, for 2 dimensional or maybe in 3 dimensional also it may work nicely, but beyond that point finding this probability of random point close to each other is very difficult, and that becomes very difficult because of the problem of dimensionality, large dimensions have these problems. So, hence most of our discussion is based on 2 dimensions. So, one of the examples of high dimension problem is this. Let us take customers who buy diapers are more likely to buy wine than average allowed supermarkets. So, what they do, they place both wine and diapers together, knowing that customers will walk between them, and in addition that is okay. So, customers walking through, one side you have diapers, other side you have wines, and once they go there, they probably have come to buy diapers only, but they will see these wine bottles, they buy that. That is okay, that is easy to understand, clustering of these two, why you want to cluster the wine bottles with the diapers. But let us say if I put a potato chips between this, what will happen? They will be also interested to buy that one also. So, this will lead to increase of sale of all the 3 items. So, this is the problem of higher dimension clustering. So, once it was single dimensions, then you add wine bottles and then you added potato chips. So, that is slowly going. So, in a supermarket which is very small, they like to cluster things together in a systematic manner, so that our eyes can go into all these different things, and that become a higher dimensional examples, higher dimensional problems. So, if you have to suggest your shopkeeper or shop owner how to increase his sale, what you will do? Think about it. It is not easy things to do. So, clustering allows you to solve this kind of problems also. So, as I told you, right. So, we have to calculate distance between the points, then only we can find out which point belong to which clusters. So, distance between 2 points, let us say A and B, is basically given by simply L1 norms, that is nothing but summation of AI minus BY whole square, like x1 minus x2 plus y1 minus y2 plus z1 minus z2 and root over. That is the standard Euclidean distance we use. That is why written summation I1 to k root over ai minus bi whole square. And we have also seen in case of KNN, you can also use Manhattan distance. That is nothing but a L1 norms. Remember this. This is nothing but sum it over I1 to k ai minus bi. This is also distance. And then you can also have max of dimension, which is nothing but L infinity norms. This is nothing but max I going to 1 to k. Max value means you have many points, distance between 2 points whichever is the max, that is what is called max of dimensions. And here it is shown between A and B, If it is A and B, this is a distance, A and B, this is a distance, you can see here, A and this is the distance between A and B. So, these are the different things. This is easy to understand. This is one distance, this is another distance. So, if you apply Pythagoras theorem, easily you can find out distance between A and B, but the other ones are not like that. Other ones are what? Other ones are different. You can clearly see that if I want to go from here to there, I go this way. That is what is Manhattan distance. Man walks like that, that is why. And max of dimension is obviously maximum distance between these two. That is what it is. If I project B here, A is there, already the distance between that. But you know, there are many other distances. This I am talking about only 3. There are many other distances I have given you in the last part of this lecture. So, broadly classified, we will talking about centroid class approach, right. Hierarchical approach we are not going to discuss today, but let me tell you that what is it. So, in centroid approach, we guess the centroid, the central point each cluster. Remember, we guess the central point, the centroid of each cluster, and then assign point to the cluster of the nearest centroid. So, that means what? If I draw this, I first decide the centroid or assume the centroid here, then all these points which are there, I calculate the distance from the centroid and then measure the nearest neighbor. That is why I form the cluster. That is understandable. That is called centroid approach. In hierarchical approach, we do not do that. We begin by assuming each point is a cluster by itself and repeatedly merge the nearby clusters using the some measure of how close or some method of distance basically, or how good a cluster the resulting group would be, like average distance of points in the clusters. That is how we do that. So, basically we merge the nearby clusters and by using some kind of a distance. That is what it is. So, here you are measuring intercluster distances, more importantly in hierarchical approaches, and centroid approach you are measuring the distance between the points in the cluster. We assume a centroid, the measure distance of the centroid with the points nearby, and that form, then we form the cluster. In hierarchical cluster we do not do that. We simply assume each point is a cluster itself. So, each point is a cluster itself, each point is, this is a one cluster, this is another cluster, this is another cluster, this is another cluster. Then we measure, we merge these points. How do you merge these points? Simply measuring distance. How close this one, how close these are, this one, how close these are, we do that. Or how good a cluster the resulting group would be. A cluster, if like these points, if it joins these 3 points, how good a cluster it will be. That is what we do. So, this is called hierarchical approach, you just do one by one. Centroid approach, you simply use a center. So, let us talk about the most popular algorithm, K-means algorithm. Again it comes K-means, right, like K-n algorithms. So, first you pick K cluster centroids, like here you see 1, 2, 3, 4, 5. Assign point to the cluster by picking the closest centroid to the point. Let us say suppose K is equal to 2 here, we assign points K is equal to 2 here, assign point 1, 2, 3, 4, 5 in that order. You can see that. So, let us, this is the 1, 2, 3, 4, 5. So, you can see that we have marked this way, but I can see 1 and 3 can be put together as a cluster, because their distances, if this is centroid, these two distances are very close to each other. Similarly, if I do a cluster around 2, I can see that if I put a centroid here, the clusters of these 2 points will be at same distance. I can do also another way, I can put a centroid here and then the distance between A 1, 2, 3 are actually almost close by, and then you can actually see 2 and 4 are close by. So, therefore, whole data I divide into 2 clusters, one with a centroid here, other one is centroid there. So, that is what is called K-means algorithm. I hope I am able to make you understand. So, remember you have only data and this is 2D, that is why it is easy. You have only data, you are only clustering based on self similarities. So, what kind of similarity exists between the data points. So, one of the ways to put a centroid, you have to choose a centroid very logically and then see the points how close they are to the centroids, and you know one can always took many centroids, okay, then that will be also leading to many clusters. That is why hierarchical cluster is much better approach. There you can merge one cluster with other clusters, thinking that each point is a cluster. So, how to initialize this kind of centroids? Pick points sufficiently far away from any other centroids. Just pick any points which is sufficiently far away from other centroids. Now, as the computation progresses, one can decide to split one cluster or merge 2 or keep the total at K. That is not possible. You can actually split one cluster into 2 parts. you can merge two clusters. So, the k remain constant because you have chosen already the k, right. K can be 1, 2, 3, 4, 5 depending on whatever you need. The test of whether is to do so might to ask whether doing so reduces the average distances. Having looked at the centroids of k clusters, we can then reassign all the points because it is very easy to reassign which is close to what centroid, right. That is what is these things. So, now I will go back to the board and explain to you mathematically how this k means clustering works. Upon explaining these aspects, let us do that. Let us assume a Euclidean system. We are assuming a Euclidean distance system or Euclidean systems. So, you have a d-dimensional observation. I hope you understand what is the dimension. It can be 1 dimension, 2 dimensions, 3 dimensions, n dimensions. So, it is a d-dimensional observation. D can be 1, 2, 3, 4, 5, 6 many things. And observations are what? Observations are like this: x1, x2, x3 goes up to xn. So, how does this k means algorithm works? Well, it divides. So, k means it divides n observations. Okay, this is, you can see these are there are n observations x to x1 to xn in a d-dimensional space, right. So, divide this n over divide this n observations with k sets. That is the k means. Remember, k is always less than n. So, you divide this n observation into k sets, that means k clusters basically, and these sets are, let us say, suppose S1, S2, S3, Sk. How do you divide it? Well, that is it. So, what we do is we minimize S, and that is what we use. I goes to 1 to k and sum it over x belong to S j x I x can be any point, not x I. Okay. This is this difference between the distance of one point from the mean. Mean is nothing but k means, okay, centroid. The mean is nothing but centroid. Okay. This is what is your centroid. So, that should be equal to, very simple. Remember what we are minimizing? We are minimizing S, number of sets, minimizing S, number of sets. That is what we are minimizing, right. And minimizing how? By looking at this distance. That is equal to J1 to k right. So, this var A, so therefore, let me write down this. So, mu I is the mean of data in SI. Okay. N is the observation of n, basically n is the number of observations. Am I clear? So, now this var is variance. Okay. In variance we use this distance, difference between this distance, okay. That is what we do, x minus mu I square mod, that is what is variance, right. So, you can clearly see that this is basically taking care of the sets x and the distance, right. I hope I am writing the things correctly, yes, correctly, correct. So, one sums become two sums. Okay, so this is the main aspects, or this is the objective function. Correct. So, how do you do that? Now, in order to solve this problem, let us assume that for each data points, each data point means x1 to xn, we introduce a set of binary indicators. So, we have to introduce to solve this problem. How to solve this problem? Okay, we can introduce set of binary indicators. Binary means 0 and 1, right. And we tell them this is R n d, sorry R n k, not d, d is different, k we are using, and this can be only either 0 or 1, and k obviously can go from 1 to k, right, 1, 2, 3 k. So, what does it mean? It means that R n k is 1 and it is 1, it is 0, okay, when j is not equal to k, but when j is equal to k, this is equal to 1. That is what is the meaning of this. It is a binary indicators. It becomes 1 when j is equal to k, and it becomes 0 when j not equal to k. So, when j will become equal to k, this will be also sk, this also will be sk, right. That is what it is. So, the moment you can do this, what do you understand? You can simplify the problem very easily. You are introducing this new variable, which is binary indicators, which tells you that whether a point belongs to a cluster, then it become 1. If it does not belong to a cluster, it becomes 0. So, what you can do then? This objective function j can be written this very nicely now. So, I can write down summation I equal to 1 to n and summation then, sorry, not I, n, because you are doing k, then R n k, summate it over x n minus mu k square. So, remember this equation what we have written, we transform into this, we added this variable R n k and this remains same x n k, okay, x n k minus mu k is this mean, x n is basically nothing but x 1 to x n, and this is the new number. So, once it becomes 0, sum is automatically going to be 0. Once it becomes 1, then only you need to sum it over. Am I right? So, this is my new objective function. So, we modify this new objective function very nicely, right. So, that is what is the useful stuff. So, it basically represents the sum of squares of the distances of each data points to the assigned mean, sum of square of the distances between the points and the assigned mean, right. That is what it tells you, it is summing over, and this sum over is basically for R n k. The first sum is basically R n k, second sum is basically for this, that is what it is doing. So, now once you have this problem, this one, basically idea is to how to get the value of R n k and get the value of mu k. And now it is very easy, R n k is basically linear equations, linearly related to j objective functions. So, therefore, we can easily find out that. So, you can clearly see that R n k is linearly related to j, basically j is a linear function of R n k. So, therefore, optimizations can be easily performed in a to form the closed solutions. So, how it is done? Very simple, if I put R n k is equal to 1, then j has some value, if I put R and K to 0, they have 0 values. So, R and K J has only 2 values. So, rather I write down very simply the equation of R and K, how to find out, then you will be able to understand. So, R and K become, so from this, to optimize the values of R and K and mu K, R and K is very easy. R and K becomes what? Becomes 1 if K is equal to minimum x n minus mu K square, double, this is basically, and 0 if 0 otherwise, y tip, any other thing. So, when this distance between point and the mean is become minimum, then automatically that point belongs to that group. So, then R and K become 1, and otherwise any other distance is become 0. When it has become 0, the objective person goes to 0, you don't need to solve at all. Only when it becomes 1, then you need to solve this kind of equations, right. So, that is the first important aspects to find out R and K. Remember why you introduce R and K, this binary indicator, because we are only deciding, once you decide, suppose I have a points here like this. So, I decide a mean here, and then I am trying to find out distance from the mean of these points. I can clearly these 4 points have similar distances, but these has a much larger distance, right, much larger distance, you can see that. So, therefore, this point does not belong to this cluster, rather this cluster will be this, where this is the mean mu. So, now in order to sort out this complex equation much easily, we introduce this binary indicator R and K. I am saying after putting my mean, whether these out of this point 4-5 points, which one will be part of these clusters, right. I can only determine simply by measuring the minimum distance of each of the point from the mean or from this mean which I have already assumed, right. This is what we are assuming at the beginning. So, I calculate distance and find out this is the minimum distance, then R and K become 1, that means they are part of these clusters, right. Now, the question is how do you decide the mean, right, how to find out the mean, right. So, once you know that R and K is 1 for particular clusters, let me erase out something, then only I can show you. So, once you know that R and K is determined, then you can optimize the value of mu K. So, very simple, it is very simple, you do not need to worry much about it, how to find out. Basically what it does is that the distance function, the objective function is a quadratic function, okay. You can see the objective function J is basically a quadratic function, right. I write down here again n1 to n, and this I goes to 1 to k or n k x n minus mu k square. So, once R and K is known, Z is basically a quadratic function, J is a quadratic function of mu, right, that is what it is. So, when it is a quadratic function of mu, how do you find out the minimum value? Basically, you can find the minimum value simply derivative of J with respect to mu will go to 0, right, that is what it is. So, take the derivative of A, if you take the derivative of J, this will be 2, okay, and R and K obviously taken 1 we have. So, this will be n is equal to 1 to n R and K we have taken derivative. So, this sum will also be there. Why are you removing that sum? Then I to 1 to k basically x n minus mu k, right, that is what it is. So, what will be mu k then? Mu k is very easily can be obtained by this expression, very simple, summation r n k x n is a function of n actually, is 1 to n divided by summation r n k. That is your optimized values of mu k. So, that means what? That means very easily, simply by using this optimization functions of this objective function, I can find out the value of r n k and value of mu k. That is what I need for any cluster to form. I need to know the mean value, I need to know the r n k values. Well, we stop here and I will come back to this descriptions in the next class again, explain it. I simply have done the mathematics so that you can try to do yourselves and understand. If you do not understand, again we will do later. Thank you.